Hi everyone, in this video we're going to be talking about inverse trig functions. This is section 4.7 in Haiku. And first I want to remind you about what inverse functions are so that we have a context for talking about inverse trig functions. So say I have two functions, f of x and g of x. We say that they are inverses if and only if when we compose them. So if I do f of g of x, I get x. So inverse functions undo each other. We first apply g to x, that takes us in one direction. Then when I apply f to that result, it takes me back to where I started. Similarly, we could do the composition in the other order. So x takes the f train in one direction, takes the g train back, and it ends up where it started, back at x. So that's the definition of inverse functions. And remember, this is how we checked that two functions were inverses. We composed them and made sure we could get x. So now let's remember the graphic interpretation of inverse functions. The graph of the inverse is the reflection of the graph of f over the line y equals x. So let's say this is my curve f. Then to get the inverse graph, I would just draw in the line y equals x, so the straight line with slope of 1 through the origin. And I could draw the inverse by just looking at the reflection. So take each of these points, put it equally on the other side. This one would go to about there and connect them up. So it looks something like that. This pink one would be f inverse. And this gave us this idea of the horizontal line test, which, if you remember, said that a function has an inverse if every horizontal line crosses that original function only once. So now let's apply these concepts to the inverse trig functions. We're going to start out by looking at the graph of sine of x. So sine of x is playing the role of our function f of x, and we want to find its inverse. So how are we going to do this? Well, first you'll notice that this actually fails the horizontal line test, because if we draw a horizontal line, it crosses in two different points. So this function doesn't necessarily have an inverse for all, or definitely doesn't have an inverse for all x values, because it fails this horizontal line test. But we could restrict the domain, meaning if we just look at a smaller set of values, maybe this section of the curve, then it does pass the line test, the horizontal line test. So if we restrict to, this is minus pi over 2 and pi over 2, sine passes horizontal line test. I'll abbreviate it HLT. So it has an inverse on that domain. So let's talk about what that inverse function is. The inverse sine function is defined by the property that y equals sine inverse of x if and only if sine of y equals x. So you'll remember from our unit on inverse functions that this just says that the x and the y switch roles. So say you plug in 2, or let's say you plug in pi over 2 into the sine function. So here's an example. Sine of pi over 2 equals 1. So that means on this side, pi over 2 equals sine inverse of 1. I just switched the x and y and changed the sign to a sine inverse. Okay, but we just said that this inverse sine function only makes sense for these values between negative pi over 2 and pi over 2. So we have to add in this restriction where our x values can be between negative 1 less than or equal to x is less than or equal to 1, because for the inverse function, the domain is going to be the range of the sine function. So it takes on, the domain is going to be the y values that sine takes. Sine takes values between negative 1 and 1. And the range, so that's the domain of the inverse. And the range of the inverse is going to be the domain of the original function. So the range is negative pi over 2 less than y less than pi over 2. So this basically says that for the inverse function, we're only allowed to plug things in between negative 1 and 1, and we're only going to get values between negative pi over 2 and pi over 2. So if we think about our unit circle, the range of the sine inverse function is all of the angles here. Between negative pi over 2 and pi over 2. So you could use a similar argument to define the inverse functions for cosine and tangent, and I'll show you those now. So the inverse cosine function is defined similarly. It says if y is the value, or let's put it this way, if cosine of y equals x, then cos inverse of x equals y, and vice versa. The restriction is that my domain has to be between negative 1 and 1. That's because the cosine function only takes y values between negative 1 and 1. And the range has to be between 0 and pi, because that's a region of the cosine function where it passes the horizontal line test, 0 to pi. Which means that the inverse cosine function is only going to take values for these angles. So you can think of these inverse cosine functions as you're plugging in an output of the cosine or sine function. So you're plugging in something between negative 1 and 1. But what you're getting out is the angle whose cosine is that value. So for example, if we do cos inverse of, let's say, 0, what I'm asking is what angle has cos blah, let's call it y, equal to 0. And we can see that that angle is pi over 2. So that's our answer. So we input values, we get out angles. The inverse tan function we define similarly. If y, so tan inverse of x equals y, if tan of y equals x. So tan inverse of x is the angle whose tan is equal to x. And we have similar restrictions. The domain of the tan inverse function can actually be all real numbers because tangent takes on all real numbers for its range. The range of the inverse tan function is going to be between negative pi over 2 and pi over 2 because that's a region where the tangent function passes the horizontal line test. So again, our outputs of the tan inverse function are just going to be between negative pi over 2 and pi over 2. So let's look at some examples now. Actually, one more important thing about inverse functions is the inverse properties. And then we'll look at some examples. So the inverse properties are basically just a restatement of these ideas. When you compose two functions, you get x. You get the input value back. But we have to be a little bit more careful because we had to restrict our view of these functions to certain domains. So the basic idea is that we want sine of sine inverse of x to equal x, and we want sine inverse of sine of y to equal y. But if we go back to our definition of sine, we're only allowed to plug things into the sine inverse function which are between -1 and 1. So what we have to say here is if -1 is less than or equal to x is less than or equal to 1, and we're only going to get out values between -pi/2 and pi/2, so and -pi/2 is less than or equal to y is less than or equal to pi/2, then these things are true. Okay, so we can say something similar for the tangent function and the cosine function using those restrictions. So if -1 is less than or equal to x is less than or equal to 1, and for cosine, it was 0 is less than or equal to y is less than or equal to pi, then we have that these inverse properties hold. So in that case, cos of cos inverse x is equal to x, and cos inverse of cos of y is equal to y. And finally, for tangent, if x is a real number and the y values are between -pi/2 and pi/2, then the tangent inverse properties hold. So when we compose tan and tan inverse, we get x, and if we compose them in the other order, we get that input value y back. So let's see how this works in some examples. In the first one, we want to calculate tan of tan inverse of 5. So first we need to check, or of -5, is this in the domain of tan inverse? So is it a proper x value? Well, it's a real number, so -5 is in the real numbers, so the property applies. So that means when I do this composition, I'll just get out my input value, so I just get -5. In this next example, we're computing sine inverse of sine of 5pi/3. So it looks kind of like this case. But we need to check that this 5pi/3 is in the proper range. So let's think about our unit circle. This is -pi/2. This is pi/2. Is 5pi/3 between these two values? No, because 5pi/3 is here, right? Nope, it is here. So that's not in this range. So we're not going to get 5pi/3. However, 5pi/3 has the same sine value as a reference angle in quadrant 4. Which one? Well, it has the same sine, so sine of 5pi/3 equals sine of -pi/3. Because if we kept going around the circle into the fourth quadrant, when we got to -pi/3, we'd have the same y value. So we can actually write this equation as sine of -1 sine of -pi/3 because of this equality. So I just replace this part with sine -pi/3. And that's okay because these two values are equal. But -pi/3 is in the proper range, and so I get -pi/3. And we have one final quick example. Cosine of cos inverse of pi is our last example. So we're looking at this case, but is x in the proper range? Well, x is supposed to be between -1 and it's supposed to be less between -1 and 1. And That's not the case here. So we can't evaluate this because it's not defined.